No issue, no issue. Okay. We were talking about rectifiers, last 4 classes, basic diode rectifiers. Main job of that is converting the AC voltage to DC voltage. And we saw the how to compute what is the DC voltage arrival, ripple factor. These are the parameters which need to be computed to find out how good the of rectifier circuit in converting the AC voltage to DC voltage. But as I told you that the output of the rectifier is a pulsating DC. Pulsating DC is this. As I told you that this is called pulsating DC. Only positive half cycle is going to half a rectifier. And also it is varying with 0 to maximum value, but it's not a constant DC. Now, many times if you wanted to have a constant DC, what you have to do is okay. Let me. We can write here, it's no issue. I can say that still this is half a rectifier. Okay. So normally we want a constant DC. We are giving 220 volts AC, correct? And 50 Hertz in India. For example, we are taking single phase voltage, AC voltage. This is given to primary coil of the transformer. Secondary, I told you it is a step down transformer. For example, it is say for example 20:1 is stepping down, correct? So that means 20 input is 220, output will be secondary output which is called VS, they call VP, will be 20 times less. Okay, in that case it can be something around 11, yeah, around 11 volts something AC. Please note that again this is voltage. We call this voltage a VRMS. Again told you, for quickly I will go through. When you talk about AC voltage, correct? If the sinusoid voltage, this is called a positive V peak. This is called as negative V peak. Both will be equal. This is 0 volt. Vertical axis is the amplitude of the AC voltage. Amplitude of AC voltage. So this is 0. This is negative V peak. Correct? So it is varying. This is called positive cycle. This is negative cycle. Already we know that. I'm not going to this one. So that means it will consider a cycle. Will consider one cycle. Will consider one positive cycle, one negative cycle. If you find V average, is that area under this curve. This is positive side. This is negative side. The V average will be 0. AC voltage, pure AC voltage, if you find the V average, which is also called VDC, is going to be, because positive cycle will be like the same amount of area. How will you find out? We'll find out integrating the area under this curve. This is one cycle. If you do the integration, I say 0 to this is 360 degree. Correct? 0 to 360 degree. If I integrate this, the AC voltage will be represented as V sin omega t. That is called V of t. This the t within the bracket says that it is a time varying quantity. AC is a time varying quantity. How it varies? The wave shape is sinusoidal with angular 2 pi f is the angular velocity, or this one, where f is the supply frequency. In India, it is 50 hertz. Correct? So this is called as AC voltage will be represented like this. This voltage is like this. We say that VRMS is nothing but V sin omega t is the where V is called amplitude. Amplitude varies from 0 comes to minus V peak. So suppose you integrate this area, you will find V average or VDC equal to VDC is nothing but area under this curve. Correct? 0 to 2 pi, or which is nothing but 360 degree, one cycle varies. V of V into sin omega t dt. If I integrate this, you will get 0 volts because AC, this is pure AC, correct? But I want DC voltage. That means but there is no use of having AC voltage. That should be rectified. We used a half-wave rectifier. The diode acts as a rectifier, correct? Diode acts as a anode, cathode. If I that, it will conduct only half. This is what we saw in the previous class. And what I am getting here is this. Okay, let me clear some area so that we can write down what is the output. So this is my input. My output is going to be like this. Half a rectifier, only half cycle will be coming. And now, if I integrate this area 0 to pi. That is nothing but 180 degree. If I remaining half is 0, because we need to integrate. This is input. Here I connect a load RL. This is what is going to be there in RL. Rectified, half-wave rectified, only positive half cycle. Now, again, if you want to find out, you have to find out what is VDC for this. VDC or V average is equal to integral 0 to 2 pi, correct? 0 to 2 pi V into sine omega t dt. But please see that if you integrate, you substitute upper lower, half of the cycle is 0. Here the voltage is 0. Here you are sinusoid, if you enter, you will get a VDC. That means you are going to get a DC voltage, which may be a constant DC voltage like this something. This is true DC voltage by integrating this half-wave rectified or pulsed DC. I told you it is pulsed DC. So this is the average DC. That means you have to find the area under this curve. Okay, that's what we saw in the previous classes, correct? V average, everything already calculated. We are given the equations also, correct? We are given the equation also, how to find out VDC equal to, for half-wave rectifier, we found a V peak divided by pi, because half the cycle only we are using. Then if you substitute that, you will get this voltage. If it is 5 volt, the average voltage, which is going to be DC, not varying. Pulsed DC, if you average, how will you do the averaging? For that, what you call a filter. To average this area under this curve, to find the average, this average value, what you have to do is, this should be supplied to a filter. That also low pass filter. It is called a low pass filter. Correct? That will smoothen this one, make an output which is a constant. That value will be this peak. This is called V peak divided by pi. That will be 5 volts means was 1.6 volts already we saw. Depending on what is input there, this is peak voltage. If you give 100 volts, 100 divided by pi, that much VDC will be coming out, which is called average. So how do you get the average? Because actually here what you are seeing will be a pulsed DC only. Next cycle, correct? So this is what is going to come if I connect a load. If I want to smooth the DC, what I have to do is I have to put correct. So diode, then I will put what you call a filter. I can use filter. This is called as capacitor. If I connect a capacitor, correct, when you give a rectified output, what you will get is a constant DC here. Now I connect load here. I added this. This is my filter. Capacitor acts as a filter. Correct? So what you will do is, when the pulsating voltage is coming, that voltage is varying, that will be supplying current to the capacitor. So from this diode, current goes, and this will be charged as positive, negative. During the negative half cycle, there's no voltage is there. So the capacitor will supply load. During positive half cycle, current will go here and also go to the capacitor. During negative half cycle, current will be supplied by the capacitor, which has already stored the energy. Correct? During this period, the capacitor is going to supply this voltage. During this time, the diode will supply. Correct? This. Okay. So I will get a VDC, which is 1.6 volts. If my V peak is 5 volts. Already we saw. So this is called filtering circuit. Many times, if you want, generally many times you want to smooth correct? That is not good for electronic circuit, amplifier, all this microprocessor, all these things want smooth DC, 5 volts or 12 volts, 3 volts or 12 volts, depending on circuit. We know bias voltage, already we saw them. That will be supplied by the filter circuit. You have to use a filter circuit. Okay. But for motor, many times you don't need this. For motor, you don't need the smoothing directly, many times you supply. Okay. So now that we saw, okay, today what we are against is full wave rectifier circuit. Okay, full wave rectifier circuit. I will draw the circuit. Please take the diagram. It's very simple. Okay. Before going to full wave rectifier, I wanted to say disadvantages of half-wave rectifier. Correct. So today I am buying some product from a shop. Correct. I'm buying for example, I am buying a soap. Correct. Particular brand. Okay. I'm using it. Suddenly, generally you say that I won't change. Nobody changes brand. Correct. They used to use all those things. You change the brand or new product, you go only if you don't like the current product, which is now the quality is not good, or they increase the price, some reason. Only when there is some reason is there, which we call a disadvantage, then only you will go for new product. If both I have X company already buying for last 10 years, Y company has come, nobody will buy Y company product just because you are started. You have to, Y company should show that the product has some advantage over the X company which is already in the market. So like that, what is the disadvantage rectifier? We calculated ripple factor. We calculated ripple factor. The ripple factor is excessive. Approximately gamma, we said gamma will be equal to 1.21. Already we showed the formula. Correct. This is generally very high. If ripple factor is 0, theoretically ripple factor gamma should be equal to 0. Correct. That is not generally possible. This is theoretical. We are going to see different type of rectifiers: half wave, full wave, bridge, and three-phase full wave, three-phase half wave. All those things. For everything, there's a formula to calculate what we saw. Already we saw that transformer utilization, ripple factor, all those things. In the half wave rectifier, the ripple factor is 1.21. Correct. This is not good. This higher the value is bad. 0 is bad. If gamma equal to 0, that is better. Theoretically, this we can say, but there's no such rectifiers available. So we need to use any one of this one. We have started with half wave rectifier. In the half wave rectifier, the gamma ripple factor equal to, already we have the equation. I think you remember that value is 1.2, which is a very high. So we call it as a excessive ripple factor. This is one of the disadvantage. Second, low rectification ratio. Correct. Low rectification ratio. The value of what we compute is 0.046 for half a rectifier. Please note that for now today we are going to see other rectifier. That time we'll see that it will be much lesser than this. Third one is low transformer utilization factor. Utilization factor, which is something around 0.287. Correct. The transformer utilization should be bigger in number. Correct. But it is 0.287, which is very low. Correct. It is not good. So next one is the fourth. This one is DC saturation and of secondary transformer. Secondary coil of the transformer. These are the 4 important drawbacks of the half-wave rectifier. This should be, gamma should be 0 or lesser is better. Transformer rectifier ratio also is 0.4 is not good. The transformer utilization we try is a TUF. Please note that already we saw the equation. In the exam, in some exam, you can expect questions from this. Some calculation, all those things. Find out for a given transformer, this is the transformer ratio, correct? Input voltage, V peak voltage is this. Compute the VDC voltage, correct? Then ripple factor, rectification ratio, utilization factor, all these things will be asked to maybe expect 3 to 4 marks some questions, correct? From this with a circuit diagram show, explain this. So these are the disadvantages. So if I wanted to overcome this, I can go to what you call a full wave rectifier. Full wave rectifier, you can see that we'll start with the circuit diagram. When I say in the exam, draw the half wave rectifier, you have to draw the transformer, input, all those things. If I say full wave rectifier, you draw this is the circuit diagram. This is the V of T, which is generally we give 220 volts, 50 hertz from the line, single phase is this one. This is VP, primary coil, and this is the symbol for, we know that the transformer. And now this is secondary. Secondary, this one, 3 wires will be coming. Generally, if you saw that previous, this one, everywhere, we are talking about, okay. Yeah. Half-wave rectifier, this is input voltage, this is the primary coil, this is secondary coil. You can see the secondary coil, primary coil, the 2 ends. I say end 1, end 2. For the secondary coil, this is end 1, this is end 2. Correct? So that means 2 wires will be coming out of the coil where you supply 220 volt input voltage and output will VS is coming out a secondary coil. It has only 2 wire. Okay. Now, if I want to use the full wave rectifier and it needs what you call a center tapped, correct? This is called as center tapped transformer. Okay, so we know that this is secondary coil I'm showing. So, for example, it has 10 turns, correct? It has 10 turns. This is one end, this is the other end. Between that, there are 10 turns are there. I will take one more wire from middle portion. This is the 5 turns. This is 5 turns. I say that 100 turns, 50 turns. Between after 50 turns, I tap one more this wire, take it out. So this is called as center tapped transformer. Secondary side, it is center tap. This is my VS. So with respect to this we can say center tap. This wire is called as center tap wire. Okay. With respect to this, for example, this is a step-down transformer. I say that I am giving 22 volts. This is 10:1 transformer. That means the input voltage will be reduced 10 times. So this is a step-down transformer. So I am going to get here across this. I will get between these 2 wires, 1 and 2, the voltage VS will be 22 volts because step-down 10 times reduction. Between this center tap wire, between these 2, it will be 11 volts. And between these 2 wire, it will be 11 volts. Please note that again. This became a reference terminal. Center tap terminal became a reference terminal. Correct? At the secondary side. Secondary side also still you have AC voltage only. I gave my input voltage, primary side. This is VP. It is varying between 0 to positive V peak. How will you calculate V peak? V peak equal to, I say my input is 220 volts. This is called a VRMS voltage. If VRMS voltage is given, the V peak voltage can be computed VRMS multiplied by √2. Correct? This I said 220 volts multiplied by 1.414. I think around 310 something will come. Maybe I don't know. Somebody can calculate this. This is the voltage. This will be with respect to 0. It increases. It goes to plus, for example, 310 volts. Similarly, then it decreases, becomes 0. It will come. This is be minus 310 volts. This is called minus V peak, and this is called as plus V peak of our single phase power supply in India. What we are saying, 440 volts, 220 volts, 5000 volts, generator, all this thing called a VRMS voltage. That means if you want to find the V peak, you need to use the formula VRMS multiplied by √2, 1.414. If you say, then that is V peak. So now, in full wave rectifier, what you will get will be, okay. Before completing, I want to complete the circuit before we will talk. Okay. So I have one diode, I call D1 diode, which is connected to the one end of the center tap. This one, with respect to center tap, top, I say the top half of the coil, I connect D1. Similarly, I connect another diode, which is called a D2. Full wave rectifier requires 2 diodes. Please note that half wave rectifier requires only 1 diode. In full wave rectifier, you need 2 diodes. Now, then what I will do is, I connect these 2 short circuit. Okay, let me clear it so that you can see it. So these 2 will be short circuited. Please see that this is the anode, this is the cathode of the D1. This is the anode, cathode is the please know that anode is connected to anode D1 anode is connected to one end of the secondary coil. Similarly, anode of the D2 is connected to another secondary coil one end. The center tapped, I said it is this one reference. Now the two cathodes, correct? A1, I say A2, C1, C2, correct? These two cathodes are shorted together and the output will be taken with respect to this. This is my V out, correct? This is my V out. So the output is taken with the reference to center tap wire. After, and the other end is the output of two diodes. Two cathodes of diodes are short circuited and it is connected to this one. This is my V out. How it will be? It will be like this. This is positive half cycle. This is negative half cycle. This is positive half cycle. This is negative half cycle. Please show that this is 0 volts. This goes to positive V peak. Correct? So same V peak. What will be the value? Plus 310 volts. Please, you see that using this full wave rectifier, I am getting the negative half cycle also. It is also comes as a DC voltage. This is again, this is output of the full wave rectifier, which is also pulsating DC. Why it is called pulsating DC? The voltage where 0 goes to 310 volts. But in case of here, it is not going to be 310. Very sorry. We are talking about the 11 volts. Positive 11. This will be negative 11. Sorry. This is going to be negative 11 volts. Okay. Positive and negative peak, because we are taking the output from center tap, this one. N to N, 1 to 2 terminal. I say this is third terminal, correct? Third terminal center tap. With respect to that, we are giving to diodes. So the output voltage will be like this. So this is going to be plus 11 volts. Okay. So we can see that advantage of full wave rectifier is both the cycles are converted to DC voltage. DC voltage means I said the value always above 0, but is varying signs are half wave, correct? But still it is a pulsating DC. It is DC voltage only. This can be given to motor also single work, but for the electronic circuit, what you have to do? You have to use a filter circuit. And if you want pulsating to smoothen, you need to add capacitor C. Now, then what you will get will be a constant DC voltage. This is 0 volts. VDC or V average of this will be like a constant DC voltage. For that, you need to add a filter capacitor. Okay. So right now we are getting. So this is the what advantage of full wave rectifier. We are utilizing both the half cycle, positive half cycle, also negative half cycle. So because of that, the VDC will be more than the half wave rectifier. Half wave rectifier, we saw that VDC was 1.6 volts when V peak equal to 5 volts. Correct? This is a V peak is AC voltage. This is pulsating. This is the pulsating. After that, you have filtered. After filtering, the pure DC will be 1.6 volts. Correct? That's what it is. But in full wave rectifier, the value will be different. Okay. So what is the equation? We say that Vs, secondary output voltage equal to V peak into sine omega t. Correct? Same input we are giving. Okay. Now the VDC in no load condition, without load, no load condition, VDC equal to 2 into V peak divided by pi. What was the VDC for the half wave rectifier? VDC for half wave rectifier, it was V peak divided by pi. Correct? Here you can see that it is multiplied by 2. Literally speaking, this is half wave rectifier output. And we are multiplied by 2. That means my VDC of the full wave rectifier double the quantity. That means if I give V peak equal to 5 volts, then VDC will be 1.6 multiplied by 2, it's going to be 3.2 volts, which is much better than, okay, which is much better than the half wave rectifier. That means my efficiency of my full wave rectifier is better. Correct? I am giving a AC voltage which is varying 0 to 5 volts peak, and again comes to 0 to -5 peak, it is moving. Correct? So it is varying like this. This is my input Vs. Correct? So my VDC after filtration, what I will get will be 3.2 volts, which is 2 times the half wave rectifier. So you see the advantage. I'm using both the half cycle, positive and negative. Because of that, I get higher VDC. Note on the formula, correct? VDC will be twice of the this one. That is very important. Okay. Then, if I connect with load, correct? VDC with load. Without load, what it means? Don't get confused. That means I am not connected to, please see that I am not connected to the load. Resistor is not shown. If I connect to load or a motor, whatever may be, it start taking current, drive. That is called a load condition. Under load, with load, VDC average can be, will be 2 into Vp divided by pi. Please note that this is output voltage, this is no load condition. Correct? Same as that. Minus IDC into RS plus RD. This voltage should be subtracted. That means this will be, correct? VDC with load will be lesser than that without load. Correct? VDC without load, we found it to be 3.2 volts. So VDC with load will be lesser by this voltage. Okay. So where ID is the current flowing from the. Okay. So I will draw this for you once again. This is my VP primary voltage. I am giving 220 volts, 50 hertz from the grid power supply, single phase power supply. Then I have the center tap transformer. Okay. This is my D1. This is my D2 diode. Both the anodes should be short circuited. Cathode should be short circuited. This is my anode, cathode, anode, cathode. This is center tap wire. In electronic circuit, if I show like this, that means they are not in current. So generally you can draw wires like this. Correct? You may think that these two, this is one wire, these two wire, they are crossing each other, touching. That means it may be short circuit connected, you can think. Correct? To avoid the confusion, generally, what they do is in electronic circuit, it is not contacting each other, they put a bump like this. The second wire goes like this. And if I connect this load, this is my RL, this is my IDC. Correct? And same as IL. Load current IDC is same. That is supplied by these two diodes. Okay. Now, this is what you will get. Pulsating DC like this. Correct? This is positive. This is negative half cycles. What I gave is input was sinusoidal voltage like this. Correct? This is positive. This is positive, negative, and this is negative. So you can see that this is negative. This is negative. This is positive. So if this is pulsating DC. So this was VP. VP. This is plus 5 volts. Minus V peak. This is minus 5 volts. Now this will be V peak positive because both are. So please see that how the current flows is that I will tell you that now. This is a positive half cycle, negative half cycle. Both is delivered to load. Correct? So I can say the VDC. Okay. This is the pulsating DC. Now, if I put a capacitor before the load like this is my capacitor. Now what will happen? I will get a constant DC voltage. VDC, correct? VDC and this voltage, okay? And without load, already we saw with load. Why we are saying with load? You see the formula. What is this? This is the resistance. Note down. This is the resistance of transformer secondary coil. Okay. What is this? Resistance of the diode. Resistance of diode. Dropped across this also. Correct? This has a resistance RD and this has RS. Correct? So when current flowing, what is the voltage drop across this? The IDC multiplied by RS plot 2, that will be subtracted from the no load condition. Correct? So some amount of power will be dissipated as a heat across the coil and also across the diode. That will be negligible. We can find out what it is. If you know the IDC, automatically RS is known, RD is known, and then you can compute, subtract from the load load condition. This is no load voltage of the full wave rectifier, and you can see that it is twice the amount of half wave rectifier. That is advantages. So 3.2 volts you will get. Out of that, some amount of voltage will drop. Anybody idea what will be the voltage drop across the diode? Because diode is conducting, correct? Both the diodes are conducting. That means there will be some voltage drop. When the diode conduct, what is voltage across the diode?
More than.
You know the silicon diode is 0.7 volts. Cut it. Now the diode is conducting, right? So you can, if you know this current, if you know the dynamic resistance or diode, IDC multiplied by RD will be voltage VD. VD is nothing but IDC multiplied by RD. And what is the voltage across this resistance? IDC multiplied by secondary coil. This will give VS. Voltage drop across coil. This gives voltage drop across diode. And we know that when the diode is conducting, it is 0.7 volts. Even if you don't know the resistance and also current flowing, you can say that diode is conducting, so 0.7 volts. So that much voltage will be dropped across this. And if you know the current, and if you know that RS, that should be, for example, this voltage equal to, for example, 0.5 volts. Okay. So what will the net final output with loaded condition? VDC with load for full wave rectifier when V peak equal to 5 volts will be 3.2 volts minus RS, I told you, it is 0.5 volts. 0.5 volts plus the diode voltage, because diode is conducting. Already I told you it will be 0.7 volts. 0.7 volts. So that I can write that 3.2 minus 1.2. Sorry, 3.2 minus 1.2 is 2 volts. VDC with load will be 2 volts. If my RS equal to this one and the current flowing through, if you know that, you can compute. Okay. Any doubts? Because in exam you can expect problem. That's why I am repeatedly saying, please take notes. And if you have any doubt, please tell me. Okay, this is VDC. VDC without load. I can say that without load is 3.2 volts. And same thing with load. I can say that will be lesser. We saw that it will be 2 volts. This is VDC with load, where VR, VS, okay, we are talking secondary voltage drop is equal to, for example, 0.5 also I told, and VD, the diode voltage equal to 0.7. These two should be added, subtracted from 3.12, then you will get VDC with load. So please say this is called average. This is how you compute. Okay. Now that you know. Okay. Next thing is now that we know how to compute VDC of the full wave rectifier in no load condition and load condition, and further you have to do, then we need to calculate what is called a ripple factor. Ripple factor, we know that is called as gamma. Gamma can be root of IDC, sorry, extremely it is IRM square. IRMS divided by IDC whole square minus 1. Take down the formula. You are maybe asked in the exam to compute the ripple factor of the full wave rectifier. Correct? Because everywhere there are formula, correct? We know that because there are two things. One is IDC and IRM, you should know. So where to compute this, where we know the IDC for full wave rectifier equal to 2 into I peak divided by pi. Okay. And IRMS, in the formula IRMS equal to I peak divided by √2. No doubt. Because to compute this, we know that. How will you find out this one? I peak. Correct. I peak equal to V peak divided by RD plus RS. Okay. This is in no load condition. In fact, no load condition. In load condition, I peak equal to Vp divided by RD plus RS plus RL, where RL is the load resistance. Okay, this is with loaded condition. For example, in the exam, I may give directly IRMS value and IDC value. If I am not giving IDC, IRMS, I give V peak and RD, RS, RL, then you can find out the I peak by using this formula. If it is loaded condition, no load condition, you can use this. In the exam, I will tell you whether loaded condition, no load condition, I give V peak and RS, RD and RL load resistance, then you can use this formula with loaded condition, you can find out. Okay, so this is the formula. But generally, if you compute, the gamma will be equal to 0.482 for full wave rectifier. Correct? Once IRMS IDC is given, according to this formula, if you compute, it will be equal to 0.482. Okay. So this is the full wave rectifier. Okay. I will continue with little more, one more slide for the full wave rectifier itself. Okay. So full wave rectifier. We already we saw another important factor, what you call rectification ratio or ratio of rectification. Both are this one. Ratio of rectification is written as 0.636 into V peak whole square. Take this formula divided by. This is arrived based on some other thing. If you go deep into each and every equation, it will take longer time. Generally, this is the equation given to compute the rectification of full wave rectifier, 0.707 into V peak whole square. Correct? 0.63, this one. This is going to be 0.81. Correct? The value will be 0.81. Okay, you can see that the rectification ratio should be bigger and better. Okay. So how it is can be arrived? So this equation, how did you arrive? The equation is nothing but PAC, which is nothing but V peak divided by √2 into I peak divided by √2 and PDC. The rectification ratio can be also written, note down. Another formula is equal to PDC divided by PAC. Correct? Rectification ratio can be, you can use this formula, 0.636 multiply V peak whole square divided by 0.707 into VP. If you have voltage, in terms of voltage or V peak voltage, still you can compute. Instead of that, you can use another formula this. Correct? Rectification ratio PDC divided by this one, where PAC in the formula can be computed as in PDC equal to 2 into V peak divided by pi multiple. You know the power equal to voltage. This is voltage. This is the current in the primary side. Correct? That is AC voltage coming out of the not primary, secondary coil of the transformer. PDC is after rectifier, after a diode. This voltage is our rectifier output. Multiplied by this is voltage multiplied by current. That is nothing but 2 into I peak divided by pi. Okay, so you can use any one of these formula depending upon what we are giving. Correct? Rectification ratio can be computed using the first formula or using this is the second formula. Correct? This is my second formula. You can use this. This is the first formula. Any one of this you can use it. Okay. Using that you can compute depending upon what parameter I am giving. Correct. So please need to read the question paper and understand and do this is for answer. Okay. So then last thing will be what you call as peak inverse voltage. Which is called PIV. PIV will be 2 into V peak. Okay. So this is also one of the important parameter. When diode is reverse bias, as already previous class somebody Andrew or somebody asked, the diode is reverse bias, how much voltage can withstand before taking Zener breakdown. Most of diodes, if diode manufacturer says that VAC can be applied, for example, 110 volts, 100 volts, for example, that means it's V Zener voltage of the particular diode will be greater than VAC, which is applied. Data sheet they say 100 volts you can apply, positive peak, negative also we know the plus or minus 100 volts, correct? AC voltage what we are supplying, AC is going to be plus or that is applied. When reverse is doing positive half cycle, no problem. Doing negative half cycle, the anode will be negative, cathode will be positive. So that means the reverse voltage applied across the diode. During the time, if the Zener breakdown voltage is lesser than 100, then the diode will start conducting in reverse. That should not allow. So generally, the manufacturer makes sure that the Zener breakdown is higher than the maximum negative peak voltage you can apply. That is all called peak inverse voltage applied across the full wave rectifier. Correct? This is called full wave rectifier. Okay. Taken? Okay. Now we'll go to the third type of rectifier. The third type of rectifier is called a bridge rectifier. Okay. The bridge rectifier circuit, first I will draw the circuit. This is my transformer input. This is my primary coil, VP. This is 220 volts, 50 hertz. I say that the transformer is 10:1. Correct? If I give 10 volt, in the secondary side, 1 volt will come. Okay. So that means this is VS, secondary voltage. So I have given 10:1 is TR, transformer ratio of this transformer, for example, 10:1. That means here you will get 22 volts. Correct? Again, please note that these are called VRMS voltages. This is also VRMS, but it is a step down transformer, 10 time reduction, 222. Now, bridge rectifier circuit needs 4 diodes. It requires 4 diodes. Please note that in the half-wave rectifier, 1 diode is sufficient. But only drawback is only positive half cycle is converted to DC voltage. Negative half cycle not utilized. So it is not good. You are wasting power. So that means I can go to full wave rectifier. If I use the full wave rectifier, I need 2 diodes and center tap transformer. That is one drawback, but it is needed. But only 2 diodes. No. I don't have a center tap transformer. I have regular standard transformer which has primary coil 2 terminal, secondary coil 2 terminal. This is 1 and 2 primary, 1 and 2 secondary. Only 2 this one, but still I want full wave rectified output. So then I will go to bridge rectifier, which is 4 diodes. This is the diagram. Draw the diagram. Bridge rectifier. Okay. So, please see the bridge rectifier 4 arms like Wheatstone bridge. I say this is D1. I call this is D2. This is D3, D4. 4 diodes. 4 diodes are connected like this, like a bridge, Wheatstone bridge. We saw resistance last semester in Mechaton. We talked about strain gauge bridges, full wave, correct? Full bridge, kind of 4 Wheatstone bridge, like same thing. Here, instead of the resistor, we're using diode. Okay, they called as full wave rectifier. Where is the output is coming out? This is input voltage. This is the AC input. AC input is applied across these 2 points, nodes. We call it this. Output is taken. This is out. VDC, correct? VDC. This is called positive. This is called negative. And I connect my load here. Load resistors. So what will be this one? So we'll draw the waveforms. It is repeating. I am showing 2 cycles. My output will be exactly same as full wave rectifier. Only thing is, please see that this is normal transfer, not center tap transfer. Secondary side only 2 wires. Okay. Now we are given this one. So this is the VS secondary. This is VDC, actually pulsating, because I have not used the capacitor. So please see that this bridge output also is full wave rectified. Both the half cycle. This is the positive cycle. This is positive cycle. This is negative cycle. This is negative cycle. This is positive. This is positive. This is negative. This is negative. Just like the regular full wave rectifier, which use center tap transformer, bridge rectifier also converts both the positive half cycle and negative into a pulsating DC. Now, if I want pure DC, VD, this is pulsating DC, correct? And if I want pure DC, that means I can say that right, VDC or V average, AVG, correct? This is the filtered. Sometimes some books they call a filtered output. Who is the filter? That means I need to connect one capacitor across the load. Output, in the output, I put a capacitor. The capacitor removes the pulsating, correct? Pulsating, this one become a constant DC. This is the best, correct? So this we go. So how will you same equation? Full wave rectifier in VDC pulsating. Where is it? This one, correct? This is the pulsating DC. This is the average DC. This is my input given to the bridge. Okay, this is input voltage supplied to bridge rectifier. The pulsating DC bridge rectifier output before filtering. This is after filtering. VDC is after filtering. This is pulsating DC is before filtering without capacitor. I mean I am talking here. Once you connect the capacitor, automatically filtered. Okay. So note down the formula here. VDC equal to, it will be 2 into V peak divided by pi. It is same as the regular full wave rectifier. The formula is same. Bridge rectifier and because both the half cycles are converted. This one. Okay. And this is no load condition. Under no load condition. That means I have not connected my load. This is not there. Okay. This is no load condition. Under no load condition. Now, if I connect my load, that means my resistor is connected. I am showing as a resistor. That's it. It can be a motor, it can be coil, anything. Correct? The RL can be a motor resistance. RL can be motor resistance or a circuit, whatever it may be. Correct? I generally represent resistor load. So if we use it, VDC with load. Right? Is nothing but V peak divided by pi minus IDC into RS plus RD. Please see that it is same as this. In fact, you should add RL also with RL. IDC multiplied by RS plus RD plus RL. RS is the secondary coil. This coil has a resistance RS. This is I call RD, dynamic resistance diode, and of course the RL is there. They are all connected in series. So you have to add all the resistance value, multiply by IDC, the current flowing here. This is called IDC, which is nothing but IL, load current. Say all are same. IDC multiplied by RS plus RD plus this one, and you subtract it from the no load. This is no load voltage minus this, automatically you will get it. Okay. Now, what are other factor we can compute? Ripple factor. Note on this formula, ripple factor gamma is going to be 0.482. The formula I said, the value, if you know, that is sufficient. Rectification ratio. Rectification ratio, RR, already we said it is RR, equal to 0.812. Then transformer utilization. The formulas are now, I'm giving the final value because once you know the full wave rectifier, it is same applicable here also. Transformer utilization ratio. Sorry, factor. It is called a utilization factor, which is called TUF. TUF equal to, it is 0.812. Okay. So these are the important parameters you need to understand. Okay. From this, you can see that these values are almost same as full wave rectifier. Full wave rectifier also, already previous slide we talked, ripple factor 0.482, rectifier 0.812, and TUF also this one. For full wave bridge rectifier, both are same. Correct? You may ask which one to use. I already told you. If you have only two diodes, correct? If you have only two diodes, correct, and you have a center tap transformer, you can connect like use it like a full wave rectifier, this circuit. No, I don't have center tap transformer, but I have 4 diodes. Then you can go for the bridge rectifier and you will get the same benefits of the full wave rectifier. I will stop here. Tomorrow we'll see other rectifiers, which is called 3-phase rectifiers. 3-phase, half-wave rectifier, full-wave rectifier. After that, we will see about SCRs, thyristors, which can be used for the converting AC volt to DC volt similar to diode, which is called silicon controlled rectifier, SCR. Also can be used for converting the AC voltage to DC voltage to control the voltage or current applied to DC motor. So many DC motor control, correct? DC motor there, but what you have, you don't have a battery. You have standard AC voltage 440, 220 volts, and you want to drive a DC motor, which is 220 volts or 100 volt, 400 volt DC motor. What I can do is, I can use thyristors similar to diode. Diode also is used for converting AC to DC. Similarly, SCR, silicon control rectifier, also convert. We will see that tomorrow, along with full wave, 3-phase, half-wave and full wave diode rectifiers, and also we'll see the SCR, how it can be used for making half-wave rectification, full wave rectification, and how it can be used for driving the motor to vary speed, the torque of the DC motor. We'll see tomorrow. If you have any question, you can ask. Otherwise, you can give your attendance. You can leave.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Take care.
Thank you, sir.
Bye. Bye, sir.
Bye.